Carbon and hydrogen have similar electronegativity values, which means that they can make nonpolar covalent bond. This means that when hydrogens are bonded to sp3 carbons, they are not acidic. However, when the hydrogens are bonded to an sp3 carbon that is adjacent to a carbonyl, we will say that those are relatively acidic. A hydrogen that is bonded to an alpha carbon will be considered an acidic hydrogen. The alpha carbons are only weakly acidic when we compare these values with an organic acid like acetic acid. The alpha carbon of an aldehyde is more acidic than a ketone, and we observe that when the carbon is flanked between two carbonyls, the acidity increases. So we have a diketone, a ketoester, or a diester that are more acidic than ketones and aldehydes. Strong bases can abstract acidic alpha hydrogens from carbonyl compounds to yield enolate ions. When a proton is removed from an alpha carbon, two factors combine to increase the stability of the product that is formed. The electrons left behind when the proton is removed are delocalized, and the electron delocalization increases stability. Electrons that are left on the carbanion form are delocalized onto the oxygen that was the carbonyl. The chemistry of the alpha carbon is important in organic chemistry, but is also important for biomolecules, where we will see also the opportunity for losing a molecule of carbon dioxide. The product is stable due to the presence of two different resonance structures. Resonance structures are not to be confused with tautomers. In a tautomer, we will have a change in the position of atoms, and in resonance structures, we will have a change in the position of electrons. The ketone enol tautomerism can be catalyzed by both acids and bases. The enolate form gets protonated to produce the enol. For its simplicity, I like to think about the tautomerism of a ketone as the rearrangement from a proton that is on the alpha position that will be transferred to the oxygen that is the carbonyl. The nucleophilic oxygen reacts with acids and electrophiles. Its protonation triggers the formation of a carbocation that will allow the deprotonation of the alpha hydrogen by the molecule water. When the carbonyl renders the hydrogen on the alpha carbon, the enol is formed. The formation of the enol is also catalyzed by a base. In this example, we have that the alpha hydrogen will be deprotonated by the base. Once we have created a carbon ion, a molecule of water that is formed protonates the oxygen, and that will trigger the formation of the enol. Enols cannot be isolated, but enolates are very useful for synthesis in the lab due to the stability because of the different resonance structures. Here we have the example of acetone, which is going to exist basically as a ketone and only traces as the enol. Opposite to acetone, the ketone of phenol exists as traces to prevent breaking the stability of the aromatic benzene ring. In the equilibrium of a 1,3 diketone, it will exist as 15% enol, and that has to do with an enolate that has two different resonance structures that are delocalizing the negative charge of the alpha carbon that is flanked between the two carbonyl with two oxygens. The more resonance structures, the greater the stability. After proton abstraction by the base, we have one negative charge that is going to be shared by two oxygens. So we have two different resonance structures. Another factor influencing the stability of this enol is the opportunity for the formation of hydrogen bond between the enol and the carbonyl. Halogenation of ketones can take place in acidic conditions or in basic conditions. In acidic conditions, only one of the alpha hydrogens will be replaced, while in basic conditions, we can have multiple substitutions of the alpha carbon. The first step of this reaction is the formation of the enol, which is followed by the addition of the halogen. After formation of the enol, the alpha carbon will add to the Br2, generating a plus charge on the oxygen. Only one of the Brs is added because this is a substitution of the alpha hydrogen. The neutral product is formed by regeneration of the acid catalyst. The substitution of the alpha carbon in basic conditions by a halogen removes all of the alpha hydrogens from that carbon. Each halogenation is more rapid than the previous one. This is because the electron withdrawing group Br on the alpha carbon increases the acidity of the remaining alpha hydrogens. In acidic conditions, the first halogenation decreases the basicity of the oxygen. This makes the protonation of the carbonyl oxygen less favorable. We can see the completion of the mechanism for the substitution on basic conditions. We start with the protonation of the first alpha hydrogen, doing a monohalogenation. We increase the acidity of the left hydrogen, and then we do a second addition of the Br. So we are getting as a byproduct 2 Br minus. The last halogenation of the alpha carbon is an excellent method for the synthesis of amino acids. In this method, we are going to start by an azole substitution of the hydroxyl group of the carboxylic acid group and do an addition of Br, a tautomerization, and a hydrolysis. Let me remind you that phosphorus is always very attracted to oxygen, or the opposite. So what we'll see is that similar than the activation in biomolecules by using molecules of ATP, we can actually make an OH a better leaving group when it is bonded to the phosphorus of PBr3. So we see in this mechanism how we are creating a protonated hydroxyl group in the carboxylic acid part. We are kicking off as an SN2 mechanism of the reaction a Br2 minus that can later, after forming a tetrahedral, kick off a big part to form the azole halide. PBr3 converts the carboxylic acid into an azole bromide, which is in equilibrium with its enol. Bromination of the enol forms a protonated alpha brominated azole bromide, which is hydrolyzed to an alpha brominated carboxylic acid. Once we have done the halogenation on the alpha carbon, we can decide what is the next step. We can have SN2 reactions by replacement of the Br, or we can use a strong base replacement of the Br by elimination to produce an alpha-beta unsaturated ketone. To ensure a complete removal of the alpha hydrogens on a ketone, it is necessary the use of a strong base. When you use a weak base, only a small percentage will form the enolate. That is favorable for condensation reactions. If we want to do an alkylation on the alpha carbon, one base that is recommended is LDA. That is much stronger base with a pKa of 38. For the alkylation of cyclopentanone, LDA will create an enolate that is suitable for an SN2 reaction. Having a good leaving group like iodine, we will have the product of 2-methyl cyclopentanone. But since cyclopentanone has 2 alpha carbons and in each two alpha hydrogens, we can get a mixture of products. The products are 2-methylcyclopentanone and 2,5-dimethylcyclopentanone. In this example, we have two different types of alpha carbons, and the amount of products will depend on what are the conditions of the reaction. The substitution can take place in the tertiary carbon, or it can take place on the secondary carbon. The stability of the enolate will be different for both. While the enolate on the tertiary carbon is more stable, the one on the secondary carbon can form faster. When the reaction is taking place at -78, the kinetic product is going to form because the alpha carbon on the secondary carbon is much simpler to be reached, it's more accessible. If the reaction is taking place at 0 Celsius, then the more stable carbon ion is going to form on a tertiary carbon, and we will get the thermodynamic product.